If you'll recall, we've been looking at graphs of sinusoidal functions, and we've had to identify 4, which is really 5 things. The amplitude in the middle, that's the vertical stuff. We also need to identify the period and the horizontal shift, that's the horizontal stuff. We also have to identify the form that we want to use, sine or cosine, and positive or negative. The horizontal shift and the sine, cosine, positive or negative is all determined by the anchor. You want to think of the anchor point, the point we choose as a starting point. That determines 2 things, the horizontal shift and whether we're going to write plus or minus, and whether we're going to write sine or cosine. Which of the 4 functions we're going to choose and what horizontal shift we're going to choose. The other thing that we need to identify is the period. If we're looking at a graph, we can observe what the period is. Or if we're looking at an equation, we can calculate what the period is by looking at the coefficient of x. So the period is either 2 pi over b. If we want to know the period, we take 2 pi divided by the number that we see as the coefficient of x in the equation. Or if we want to write the equation, we take the period that we observe, and 2 pi divided by that period is the coefficient that we put on x. We can also notice that 2 pi is equal to b times the period, but that doesn't really give us information that we can put into an equation or draw on a graph. So that's not quite as useful, but it is an equivalent version of that statement. And there was only one left, so I figured I'd include it. It's like when you see an ad on TV, when there used to be ads on TV for like a compilation album called AM Gold. I don't know if you knew this, but before you could make your own mixtape, you had to buy people mixtapes from the television. And they would order AM Gold, and they would list all the songs on this 5-cassette set of AM hits from the 60s and 70s. And they would list like 50 songs, and at the end they'd say plus 3 more. I'm like, oh, dude, you just listed 50 songs. Just list the other 3 songs. Why are you not telling? Because it was just like a scrolling list of like 50 songs, and then all of a sudden it's like, plus 3 more. I'm like, oh, dude, it was 3 more. Speed the list up a little bit and tell us what the other 3 songs are. Which could only lead me to conclude that those other 3 songs are really bad. I say, no, if we list these songs in the list, then people will not buy this album. If they list these 50 songs, and like song number 51, We're Not Gonna Take It by Twisted Sister, that'll cause people to not buy the album. They're like, oh, well, I was gonna get it up to that point. So they said, we can't put that one on there. So there are 3 songs that were on the list that would keep people from buying the album. So they didn't list it. That's all I could think of. But that would be me like eliminating this one. I wanted transparency. I'm like, oh, here's another way you can say that statement. The period times b is equal to 2 pi. Of course, that was a risk. Maybe like AM Gold, you're going to drop the class. You're like, oh, nope, you wrote that one. That's the deal breaker. This was the deal breaker. I'm fine with 3 is equal to 6 divided by 2, and 2 is 6 divided by 3, but saying that's equivalent to 6 equals 2 times 3, unacceptable. Unfollow. Unsubscribe. Or maybe not. The form of the equation that we're writing we always decide whether we're going to write plus or minus, and then the coefficient a. And then we're going to write sine or cosine. And then we're going to have parentheses. And then we're going to have the coefficient of x. And then I like to be able to read the information right in the equation. So I put another set of parentheses and write x minus. And that's where we write c. And then close the parentheses around x minus c. Close the parentheses that form the argument for your trig function. And then you can write plus d. You don't have to force D to be positive. Yes. Yes. We learned, we use sine and cosine because it fits best. There's no vertical asymptotes with sine and cosine. If you saw in section 4.3 where we talk about tangent, cotangent, secant, and cosecant, there's a bunch of vertical asymptotes because those functions are all given by these ratios where the denominator is 0 sometimes. With sine and cosine, that's not a problem. Sine and cosine have this shape, no vertical asymptote, so it's a little bit easier to deal with. So here's what we want to look at. I like to take this opportunity to look at what's happening to the x and think about things in terms of order of operation. I want to look at this function and I want to think about the order of operations on x. I want to think about what happens to turn x, our input x, into the output y. I want to imagine if we plug x into this function, what is the first thing that we would do? And I want to use that to compare it to what happens to the graph. So let's suppose that we start with an x. If I plug in a number for x, what's the first operation that we would perform? Subtraction. The first thing we would do is subtract c. So I'm going to write that this way. So the first thing, I'm going to say subtract c. After we subtract c, we've got this quantity. What's the second operation we perform? Multiply by b. So the next thing we're going to do, I'm going to summarize by saying multiply by b. What's the third operation that we do? Sine or cosine, plus or minus, sine or cosine. We take the sine or cosine. So I'm going to summarize that just by saying trig. So we do the trig function. And I'm going to put parentheses because we apply trig, the trig function to whatever we got after we subtracted c and multiplied by b. After we do the trig function, what's the next operation? Multiplication by a. So next, we multiply by a. And what is the last operation we do before we can write down what is d? We add d. And once we've done all these things, x, the input x has become the output y. So here's what we want to observe. Notice that there were two operations before we got to the trig function. There were two operations after we did the trig function. The two operations before the trig functions have horizontal effects. The minus c, that's telling us where the our horizontal shift. Multiply by b tells us the period. That's our horizontal stretching or compression. So the two operations before the trig function are horizontal effects. And the two operations after the trig function are vertical effects. So two operations before the trig function are the horizontal shift, and the horizontal stretch. Then the trig function happens. Now anything, any effects that we see on the graph are going to be vertical effects. So multiply by A, that's our vertical stretch. And plus D is our vertical shift. Before the trig function, horizontal stuff. After the trig function, vertical stuff. The first time we encountered this idea about horizontal shifting, and stretching, and vertical shifting and stretching usually happens in trig right now because we have such a great function to work with. Sinusoidal functions are nice and contained. It's easy to see what's going on vertically stretching, vertically shifting. And once we start seeing one cycle, we can imagine that shifting and stretching. So the first time we encountered this kind of idea, these effects on the graph, before and after, we're dealing with trig functions. That's the most common thing. But we can apply this to other kinds of functions. This before horizontal, after vertical also applies to other kinds of functions. It's just the first time we encounter it is with trig functions. The other thing going on here is that multiplication is a stretch. And addition is a shift. These ideas all apply to other kinds of functions. They apply in general. We can apply these ideas to other kinds of functions. So for example, let's think of the function y is equal to x squared. What shape does this graph have? It's a parabola. A lot of times people describe a parabola as a U-shaped graph. We need to get rid of that. It is not a U-shaped graph. Stop thinking of it as a U-shaped graph. It is a rounded V-shaped graph. I know you're thinking, dude, aren't those the same thing? And it is absolutely not. When you draw a U is vertical on its sides, right? It's like two verticals with a roundy part at the end. And also there's like a tail, but let's ignore the tail for now. I don't know why that didn't disqualify U from contention right from the get-go. But not everybody puts a tail on their U, so I guess that's it. So like U, it's like U with a tail, like that. I mean, that's right out. That does not look like a parabola at all. Yeah. But the problem with U, not you, y'all have completely different problems. I'm just kidding. The problem with the letter U to describe a parabola is what's going on the sides. Those sides are like vertical. That's bad. That's not parabola. Vertical sides. not parabola. No, not parabola, vertical sides. But a V, sides aren't vertical. That's more parabola. The parabola keeps going on forever in both directions. It doesn't, it spreads out infinitely in both directions. It doesn't go vertical and then just like stop horizontal. We can't contain a parabola in between two vertical lines. They get very, sides get very steep, but they never go vertical. The problem with the V is that the V is very sharp at the bottom. That's more absolute value. So you go for the rounded V. So you want these, right? But you kind of want it round at the bottom. And then the sides are going to get steeper, but never go vertical. Now we're talking. Rounded bottom. The sides get steeper, but never go vertical. Sides are getting steeper, but they never go vertical. This is all just me justifying rounded V instead of U. It really doesn't matter. I guess too many people say probably the U-shaped graph just because of the round bottom edge. That's terrible. The rounded V's. Sides don't go vertical. Let's take a look at our graphing calculator, since our graphing calculator is so much better at graphing. Oh, the graphing calculator that I think I closed. Yep. So here's our graph y equals x squared. It's going to be our base graph. Let's make this a make that one stand out. There's our y equals x squared. Now we're going to start applying shifts, horizontal and vertical shifts. Let's start with addition, because addition is our most basic thing. So let's add a horizontal and vertical shifts. Oh, right. I don't have two screens. I was writing stuff, so for those of you at home. So I'm going to add in a horizontal shift, and I'm going to list it like I listed the horizontal shift with our sinusoidal functions, x minus h. And that's where we get the square. And then we'll add k. So we'll add sliders, and we'll put them at 0. All right, so here, if h and k are both 0, we have 0 horizontal and vertical shift. Notice that the operation that I'm using to make a shift is addition, and the additive identity is 0. The additive identity is the number that doesn't do anything with addition. So in that case, 0 is the additive identity. So adding 0 doesn't do anything. If I change the value of h, since it's inside with the x, it happens before the square, that's going to produce a horizontal shift. So changing the value of h makes the graph move left and right, but maintain its shape. No whammies, no whammies, big money, stop. I missed it a bit. So the plus k is after the square. So first we subtract h, then we square, that's the function that we're investigating. And third, we do the plus k. So if I put that into motion, that's going to move the graph up and down. Calm this down a little bit. So now that my shift on the outside, my addition on the outside is moving the graph up and down. Notice it's hard to see because of the resolution, but it's x minus h squared. And that should be a plus k. I did not see the plus. It's because my computer and the projectors don't get along very well. And the projector's like, oh, I'm not going to display all of your pixels. My computer's like, oh, well, fine. I'm only going to give you some of the pixels anyway. And so they're arguing. It's a whole digital thing. I don't want to get in the middle of it. We'll start moving this around. Now we can see how that DVD screensaver thing works. All it did was take the coordinates of the center and either add or subtract from either before or after. It also randomized it a little bit more, so it wouldn't make the same rectangle. Any questions? How's everybody okay? Not bad. Missed a little bit. Now let's look at what happens if I do some multiplication before the square and multiplication after the square. I typed those in the wrong order. Oh, I put to the x. That's a much cooler. Look how cool this graph is when the x's go negative. It's like all confused. When x is positive, everything's cool and it's this nice graph. Let's make this a nice color. When x is positive, we get this nice cool graph. Everything's cool. It's like, oh yeah, no problem. That's because I have like a 1/2 power of x. When x is positive, that's okay. We get an actual number. But if you try to do a 1/2 power of a negative, you're trying to find the square root of a negative number, and that's not a real number. So it can't graph all this stuff in here. It's like, I don't know what to do. Yeah, so like all these little gaps, the graph is like jumping into the complex plane and we can't see it because we're only looking at the real plane because we're silly little 2-dimensional creature or 3-dimensional creatures looking at our pathetic graph that can't see the complex plane. But let's make this, let's keep it real here and make that a square. That's what I try to do. Now, notice that the default a equals 1 and b equals 1 mean our graph is just the original x squared, our original parabola. This is because my changes now are multiplication and the multiplicative identity, the do nothing number through multiplication is the number 1. Multiplying by 1 doesn't do anything. Now, if I set A in motion, we know that this is going to stretch or squish the graph vertically. So here the graph gets squished when A goes up and then gets flattened when A goes down. And then when A goes negative, it changes direction. This is stuff that we knew about parabolas already. If A is positive, the parabola opens up. If A is negative, the parabola opens down. And when A is 0, Well, everything is zero now. Y is equal to zero, and flattens out. But the closer A is to zero, that's as close as the slider will get, 0.2. But if I change this up a little bit, so here's normal, here's A decreasing down to zero. We can see, now that it's going a little bit slower, how it just keeps getting flatter and flatter and flatter the closer we are to zero. So here's where A is 0.3, 0.1. There we can see, it doesn't seem to jump off or to pull off of the x-axis at 0.001. It doesn't seem to pull off of the x-axis until we get x out to 10 or so. But if we zoom out, I'm not gonna, if we zoom out, we can still see that we're getting this parabola. It's just very flat because A is so small. And if I pull A even smaller, it just gets flatter and flatter. We're way zoomed out now that our original parabola is almost collapsed. But we're still getting that parabola shape. Yes. A, in this case, is in charge of the vertical stretching. And when A drops negative, it reflects the graph, just like when we change the coefficient from positive to negative on a cosine, we change our anchor from this top to the bottom. That's reflecting. B is going to be compression horizontally. But an interesting thing is going to happen with B. We're getting pretty far out there now. Yeah. So now we've gone, so this is 2 times 10 to the 6th. Now I'm zoomed out so far, my original parabola, we can't even see it anymore. It's collapsed down onto the y-axis. We can see it a little bit up here if we scroll up, that the line is just thicker. What is times 10 to the 7th anyway? What's times 10 to the 6th? That's one that we should recognize. What's the common word for 4 times 10 to the 6th? 10 to the 6th is a million. So this 4 times 10 to the 6th is 4 million, 2 million. And that's the scale down here, 2 million, 4 million, 6 million. I don't know. I think there's been a lot of inflation. So like teams no longer at the end of the game, 2, 4, 6, 8, other team, gray, other team. I think there's been a lot of inflation. So like, oh, 2 million, 4 million, 6 million, 8 millions. Who do we appreciate? Late stage capitalism. But anyway. But if we go back to the default, we can see our original parabola, but it doesn't look like our point. I can't count the zeros. There's too many of them. That where A is 0.00, a bunch of zeros, 1. A is so small, it's so close to 0, it looks like it's just flattening out the graph. We can't see the difference. This is like us, by the way, standing out in a plane on the earth. It looks like everything is flat. I've been to Chicago. Everything is flat. It's like creepy flying into Chicago because it just looks like it goes on forever. But we know it doesn't. We're just not looking far enough away. We have to zoom way out to see how things are curved. I don't know if we don't have to go this far, but the farther out we go, the more curve we can see. Oh, I've messed this all up now. Let's reset A back to 1. Remember what was happening when A was increasing? we were stretching the graph vertically. When A was decreasing down towards zero, we were compressing the graph vertically. When A got to zero, the graph went flat. And when A went negative, the graph flipped down below. Let's see what happens if we start messing with the value of B. So we see compression and we see stretch. And then when B gets to a large value, it looks like the graph goes wider, it's stretching out, but then B turns around. It looks like it bounces off the y-axis. Notice that it's never going negative. The values are never going under the graph. Take a look at the structure. Look at the number that we're changing. Y equals 1 times B to the x, A times the square of the product of B and x. Saying things in words is just awful. How come the graph isn't going negative like it was when we were changing the values of A? Yeah, we've got this exponent of 2. That exponent of 2 is making everything positive. So even when B goes into a negative value, that negative gets squared and becomes positive. Even exponents are like that annoying friend that's always like, cheer up. Well, sometimes sad is the correct answer, right? You don't just get to cheer up. I mean, there wouldn't be no depression if you could just like, oh, cheer up. And then like, oh, nice. I'll feel better now. It's like when someone's angry, be like, oh, calm down. Like, oh, whoo, thanks for saying those words, because now I'm not angry anymore. I mean, that's just not how emotions work. I've realized that if I'm angry and someone says calm down, it has the opposite effect. It makes a calm up, which definitely seems backwards. If someone is angry, their calm is already down. You want them to calm up. You want to up their calm. You know what I mean? This tells me that angry and calm is a horizontal shift, right? Because multiplying by B bigger than 1 compresses things in. Multiplying by B when it's less than 1 stretches things out. So when we say calm down, we are acknowledging that anger is a horizontal shift, or a horizontal stretch. What are we talking about? Oh, yes. We've got this even exponent, and that's why we're just seeing it flip around. Now, what's happening is it is flipping around, but we can't see it flip around because of the symmetry over the y-axis. So it is actually turning, but the left side becomes the right side becomes the left side, and everything is the same. Let's see what happens if I go back to 1. Go back to 1. I had it. Let's switch to a graph that will respect some negatives. Let's change our original up. Oh, not 23. That's a little too much. Let's see what happens if we put B in motion. Now we can see it, but instead of flipping up and down, it looks like it's flipping right to left. It's not rotating. There's no z-axis. There's only x and y. We're being three-dimensional beings looking down at the plane. The plane doesn't know what's going on. They don't know anything about no z-axis. It's just like the four-dimensional beings that are watching us in the fourth dimension and just making fun of us because we can only perceive in 3 dimensions. You know, like, oh, hey, have you seen they use time as the 4th dimension? Like, oh, time? What about meters in the 4th dimension? I don't know, man. That's what they're doing. And then meanwhile, sitting outside of that are 5th dimensional creatures saying, look at these people in the 4th dimension. So what's happening is that when B goes to 0, that flattens everything out. But then the left side becomes the right side, and the right side becomes the left side. Because the -6 over here on the -6x gets multiplied by a B that's negative and becomes the +6x. So it's flipping around the y-axis. Just like when A changed sign, it flipped around the x-axis. It's vertically reflected. Now it's horizontally reflected. Any questions? Nah, it's just a cubic. If there is a name for it, I don't know what it is. Now you might notice, hang on, man. I'm seeing the same kind of thing because if I put B back to one, thank you. And I put A into motion, isn't the same thing happening? Why is the same thing happening? Isn't this also reflecting left and right? All right, so if A is negative, then it looks like that. And then when B is negative, it makes it kind of go back to the right shape. But when A is positive, it's this shape again. What gives? Why is this happening? Why is that horizontal reflection and the vertical reflection, why do they look the same? Why does the horizontal reflection and the vertical reflection look the same? That didn't happen with our sines and cosines. Because it's all multiplication. If I make B negative, let's switch over to the writing. If we look at our function, y is equal to a times b to the x cubed. If a is negative, if a is -1 and b is +1, then we get this vertical reflection because our graph looks like y equals a times b to the x. But if I make a equal to +1 and b equal -1, then horizontal reflection. But because of the symmetry in our graph, that looks the same. I'd write y equals 1 times -1 x to the third. -1 to the third is still negative x cubed. So the symmetry makes the vertical reflection and the horizontal reflection look the same. All right, let's take a break and come back and talk about more graphs. Oh no.